Hey everyone. As promised, in this video we're going to talk about the Lennard-Jones potential energy. The Lennard-Jones potential energy is a potential energy that describes how two neutral particles interact when they're next to each other. By neutral, we just mean that the particles do not have an electric charge. They're not positive or negative. It's not super important that we understand where the Lennard-Jones potential comes from, at least in terms of the individual particles. All that we know is that when we bring two particles close to each other, they sort of grab onto each other. They form a bond. Their behavior in this bond is going to depend on the details of the Lennard-Jones potential energy. By understanding the Lennard-Jones potential energy, we're going to be able to understand how particles behave in substances. And by understanding how particles behave in substances, we're going to understand how thermal energy and bond energy work. For example, we're going to be able to see how just knowing a few things about how individual particles behave is going to allow us to actually compute the specific heat of a substance. We're going to build a model for specific heat, whereas up to this point, specific heat has just been a number that we plug into our equations. Now, to understand how the Lennard-Jones potential works, we just have to see it. So let's go to the whiteboard. Before we start talking about how particles interact, we need to ask a more basic question. What are we talking about when we talk about a particle? In this course, we're not going to use a super sophisticated model of a particle. You could study particles as like your entire job, and you would never know everything there is to know. But for our example, a particle is just the smallest amount of a thing that you can have. For example, a particle of water would be a single water molecule. A particle of sodium would be a single sodium atom. Now, of course, we know that atoms and molecules come in a lot of different shapes and sizes. But for our purposes, we're just going to imagine particles as little spheres. Just like this. These two particles are sitting next to each other, and they're interacting in a way that we'll see in a moment. Again, this is not a very sophisticated model of a particle, but it's going to be good enough for everything we're going to do from here on out. Now, let's see how neutral particles interact. As I said, they interact through something called the Lennard-Jones potential energy. It looks like this. Now, you've already seen this in DL. Let's take a minute and actually try to understand what it's telling us. The first thing to note is that the Lennard-Jones potential energy is just a potential energy. Everything we know about potential energy here applies. What makes it very different, though, is that it kind of has a weird shape. If we graphed gravitational potential energy, it's just a straight line. If we graph spring mass potential energy, it's a nice parabola. This potential energy is a little bit different. But we can still use everything that we know from studying those first two potential energies to understand what's going on here. For example, we know that on a graph of potential energy, the force that a particle feels from that potential energy is always going to be in the direction of decreasing potential energy. So, for example, if we asked what kind of force would a particle feel if it was sitting here, the answer would be it would feel a force to the left, because if you move to the left from that point, the potential energy goes down. On the other hand, if you put a particle over here, it's going to feel a force to the right, because if it moves to the right, its potential energy goes down. Now, a couple things to consider. First off, this is actually not a potential energy graph for a single particle. It's a potential energy graph for two particles. The Lennard-Jones potential describes the way that two particles together are going to interact. So the distances on this horizontal axis is actually the distance between two particles. And the energy on the vertical axis is actually the amount of potential energy that the two particles have together. Now, notice something interesting. I've not actually said what kinds of particles these are. It probably doesn't surprise you that different kinds of particles have different interactions. Some of these interactions are very strong, some of them are a lot weaker. But for all the particles that we're going to study in this course, the potential energy graph takes the same shape, just this shape. But we've done something that makes this graph really general, meaning that we can use it for any pair of particles. We've done this by being clever about the way that we define our axes. Let's look at what the horizontal axis is. The graph says that it is the center-to-center separation, r, in units of particle diameter. Well, what does this mean? Well, remember how we are modeling our particles as just little balls? Well, every circle, every sphere has a diameter. It's just the distance across the circle, going through the center. To say that the horizontal axis of this graph is in units of particle diameter means that if you had two particles that were at 1.5 on this graph, then their actual distance would be just 1.5 times their diameter. If the particles were at 2 on this graph, then their real distance would be 2 times the particle diameter. 3 would be 3 times the particle diameter, and so forth. That way you can use this graph for any pair of particles no matter what their diameter. Once you want to know the actual measured distance between the particles, though, you just multiply the number on the horizontal axis by the diameter of the particles. What about the vertical axis? Well, we know that this is a graph of potential energy, so the vertical axis should be in units of energy. But what does it say? Potential energy in units of the well depth, epsilon. The well depth is just a number that describes how deep this dip is. It's called a well for a sort of obvious reason. It's this deep hole, if you will, in the potential energy. Particles are going to tend to fall downwards into the hole and bounce around in there. But saying that the vertical axis is in the units of well depth is the same thing as saying that the horizontal axis is in units of the particle diameter. The well depth is just a number. It's in energy. If the energy of the particles is -1 on the vertical axis, what we actually mean is that the particles have -1 times the well depth of energy. The well depth is just a positive number in joules. You just take that number, the well depth, and multiply it by the number that you get from the graph. And that tells you how much energy the particles have in joules. So let's pick a point and see how this all works together. Let's say that we had some particles that were sitting right here. Remember, this graph represents the potential energy for two particles together. So we're always talking about two particles. We can get two pieces of information from this graph. First, we can figure out how far apart the particles are, and second, we can figure out how much potential energy they have. This dot is located at 1.5 on the horizontal axis. This just means that the particles are 1.5 times their diameter apart. Their diameter is just going to be a number in meters. And so you just take that 1.5 and multiply it by that diameter in order to calculate the exact distance. And what about their energy? Well, on the vertical axis, this point lands at -0.3. If you had the well depth of the particles, you could find the potential energy just by multiplying this -0.3 by that well depth. Again, the well depth will be a number in joules. And so -0.3 times the well depth will also be a number in joules. What would happen if we had two particles that were being held at this distance apart and not allowed to move, and then we released it? Well, in a lot of ways, this is just like a spring that's been stretched. The particles are going to be pulled back together. We can see that based on the graph. We know that the force that the particles feel will be in the direction in which potential energy decreases. When the particles are sitting here, potential energy decreases by moving to the left on the graph. And so the particles will feel a force in that direction. But what direction is to the left when it comes to two particles? Well, remember that the horizontal axis of this graph represents the distance between the particles. To the left on this graph means to a smaller distance. So the particles are feeling a force that is pulling them closer together. If instead the particles were sitting over here, they would feel a force to the right instead. A force to the right on this plot means a force that is increasing the distance between the particles. It's pushing them apart. Now, we're going to get lots more opportunities to practice with the Lennard-Jones potential. We're going to use the Lennard-Jones potential to better understand how particles behave in substances, and we're going to use that to understand why substances have some of the properties that they do. I want to reiterate one thing here. The Lennard-Jones potential energy is just another potential energy. I know it has a bit of a weird shape. We haven't really seen anything that looks like this before, but everything we know about potential energy still applies. If you give an object some potential energy and then release it, some of that energy will be converted into kinetic energy and the object will start moving. It's the same thing with two particles. If we pull the two particles farther apart and release them, they're going to move back together. If we push them too close, they're going to move back apart. And the second thing is that energy conservation still applies here, just as it has before. If you have two particles that only have potential energy and kinetic energy, and you figure out how much their potential energy is changing by knowing how their distance is changing, you could use that information to figure out how their kinetic energy is changing, because energy is being converted from potential energy to kinetic energy, just as it has in many examples in the past. Now, we're going to learn a lot more about the Lennard-Jones potential over the next few weeks. And as I said, understanding this will help us better understand how substances behave. That's all for this video. See you in the next one.